Today we're going to review Numpy and a little bit of programming that you might have forgotten. Alright, so the first step is to import Numpy. So let's do so. And we're going to import it as NP. Alright, it's connecting. Give it a minute to start up. Alright, we're connected. This is our virtual computer, by the way. It tells us how much RAM we're using, how much disk space, and how much hard drive disk space. Alright, so Numpy, its big thing is the array. That's like its version of the Python list, but much faster and geared towards numerical computations. So we have our array here, and inside the array, inside between these brackets, this is the Python list. Very slow, but easy to use. You can always add to it and take away things from the middle, and Python will take care of all the details. But the array is kind of stuck. Its size is stuck, so you can't just take things away or add to it without really recreating a whole new array. So make sure when you create arrays, they're big enough for your application. Alright, so ARR is an array, and here's what it looks like when we print it out, and its type is called Numpy n-dimensional array. They come in different sizes, not just, this is a one-dimensional array. But usually when you want a matrix, you use a two-dimensional array. Alright, so the length of an array is just the number of elements in the array, 8. Just like Python there. And just like a Python list, notice we access it with a subscript notation here. So we can say for I in range of n, print array I. And the other way to access the elements in the array, which is common in Python but not so in arrays, is to just say for w in array, print w. See, they both give you the same answer, but typically when you use arrays, you actually want the index. You want the I. So, for example, if you want to know what the first element of the array is, so that would be a 1. If you wanted the element that, it's really the 0th element is the first, of course, so we might want to say the 0th element. The second element is 3. So you can access each element of the array. Alright, so when you do calculus type math, differential equations, things like integrals, derivatives, you typically want to approximate an interval. So you can't, of course, have the entire interval, though there are computer systems that can do math on intervals. But we're going to just keep with discrete. We're not going to have the whole interval, we'll just have maybe 10 points in the interval. So let's take a look at this. Linspace 0, 1, 10. So looking at the output here, 0 is where you start, 1 is where you would end, and 10 looks like the number of elements in this array. And That means we start at 0, we end at 1, and we go there in 9 steps, because we have to count the 0 step, the first step, and the last step. So it's probably not exactly what we wanted here. So we probably wanted our delta x to be 0.1, but what happened was delta x was 1/9. So what we would probably want to do is this. We'd want to have our linspace go from 0 to 1, but with 11 subdivision points. And that takes into account the one at the beginning and the end, and then you have your delta x would be 0.1 like we wanted. So this is how you would get a nice mesh. And hopefully you remember this kind of thing from integration in calculus. You have your subdivision points x0, x1, x2, x sub n. In this case, x sub 10 if you start counting at 0. And your delta x is b minus a. Right? So your delta x, formula for delta x, and this is how you type math, by the way. Use a $sign. Delta x is equal to fraction b minus a over n. And then you hit the $sign again, and that converts it to math, and then when you unclick here, you just see it in the nice math notation. Okay, so now let's try to use this to do a little bit of graphing and calculus and stuff. Alright, so I want to go from 0 to 6, and I want 21 subdivision points. So delta x would be 6 over 20. 6 minus 0 over 20. So running these, we see that we get this is our mesh. Sorry. All right. So we can't see x. I didn't display x. So if you want to see what x looks like, we would print x. So here's x here. So 0, 0.3, 0.6, all the way up to 6. And then here's the neat thing. So I want to take the sine of x. I want to use the computer programming Python to work with a function, sine of x. You have to get used to the idea that a function is a set of ordered pairs. That's how you actually define it in more advanced math. There's an input and an output. So the input of 0 is an input, and the output is also 0. 0.3 is an input. Its output is 0.295. So that's how you can think of the function. And on another level, you could say x is this list of array of numbers. Y is the sine of x. So what you did is you just took the sine of every number in your mesh, in your x array, that's your mesh, and you did it with vector math. So vector math means you could also think of x as a vector, like a vector with 21 numbers in it. And vector math means when you do an operation, you just do the same operation on each element of your list, of your array, of your vector. That's how modern artificial intelligence works. These new chips, graphical processing unit chips, can do these operations on a vector scale and do like thousands of things at the same time. That's how they become so fast and so good at what they do. Alright, so we have our x versus y. So now let's plot. So we could always plot a function, x versus y, and connect the dots, and here's what you get. So notice it's the sine curve. We're going from around 0 to 6, so not doing a whole period of 0 to 2 pi. Alright, so now comes a little bit of complicated stuff. Let's say we wanted to find the antiderivative. So when I say the antiderivative, what I'm thinking of is this antiderivative right here. The integral from 0 to x of f of t dt. So that would be the area function. And remembering the fundamental theorem of calculus, the area underneath the curve as a function is an antiderivative. Okay, so how do we go about computing this integral? So the idea is we're going to let x vary over some mesh, some mesh array, and for each value of x, we're going to calculate the area underneath the curve from 0 to x. And then we're going to store that as the output for the new function. So we have our original function, which is going to be lowercase y, which you can see here is this graph. Notice I plotted directly x versus f of x. You could do that because f of x is the same thing as taking the function of every x value. So same thing as just plotting x versus y. Alright, so how do we do this? Alright, so step one, we need basically the mesh of all the numbers from 0 to 6. Notice I let n equal I let n equal 100. So that means there's going to be 100 points in the in our mesh. Now take a look at line 2 here. This is a neat way to define functions in Python. It allows you to just define a function like you would use it in calculus. So you say, see this lambda? This is a keyword. It's called a lambda function. So you say f equals lambda, and then I say, what happens to x? Well, x is mapped to the sine of x. And you should note that Numpy vectorizes virtually all of its functions. Like if you just wrote a function yourself, it may not be vectorized and it wouldn't work. You might have to vectorize it yourself by defining it on an array. So Numpy already does that, which is one of the nice things about Numpy. So this allows you to just say y equals f of x. And then if I want to change the function, I could just change this one line of code here, and then all the work would be the same. So for example, if I change this to cosine of 2 times x plus 1, it actually vectorizes this 1. It's called broadcasting. And it literally adds 1 to every point in your mesh. So take a look. So now I could just keep the same code, I just had to change this little function here. Alright, so I want to integrate this. So first, let's see what the answer is. This is the previous answer when I integrated the sine. Notice it's basically the integral of the sine is negative cosine, right? Plus c. The plus c is actually, looks like something like a plus 1 here. Alright, mistake. So Simpsons is not defined. That means I didn't load it properly. So I forgot to run this right here. So I had to import the Simpsons rule. Remember from Calculus 2, this is how you could do numerical integration semi-efficiently. Alright, try it again. Alright, and there is my antiderivative. Notice it starts at 0 because there's no area from 0 to 0. Okay, so let's see how does this work. So this is a little complicated, as I mentioned before, so stay with me. Alright, so X is the mesh partition from 0 to 6 using 101 points. Remember, n is equal to 100. Okay, now capital Y is where I want to store my answer. That's where I want to store the Y values for the antiderivative. But I don't yet know what they are. But I need a spot for each X value, right? So there's a couple ways to do this. I could create an array of all zeros, but I have to make sure I have exactly the same amount as I have here. So instead of that, what I did is I just made a copy of X. I just made Y a copy of X, but I'm prepared to change every element of this array. See, just to see what Y looks like, let me just show you. So I already defined Y, so I could, even though I'm above it, I could still print it because it's already been defined. See, this is Y right here. What I could do is I could just say U equals length of X, and let's see what that is. All right. So it's 101. Well, I knew it was 101, right? Because that's how we defined it in the first place. We defined it to be n plus 1. So what I could have done is I could have just said, you know, Y is equal to np.zeros 101. And then, if you notice, if you take a look at Y, it'll be 101 zeros here. Alright, so we don't need this. Let's trash this. And let me run the original one again. Okay. Alright, so here's the code. Q is the length of X, which we know is 101. So for I in range of 1 to 101, but remember, we only go to actually 100. We always go one less. T is the linear space from 0 to the X value, the ith X value. And I want to use 101 subdivision points to get there. So notice what's happening with T. So let me see if I can give you a little example here. All right, so let's say I is 50 for the moment. Then let's see what x of I is. 3. Remember, I'm going from 0 to 6, so 50 is right in the middle. Makes sense. So what I do is I define t to be the mesh that goes from 0 to 3. Right? So look at this here. And then if you print t, see we go from 0 to 3. Remember, we want to integrate only from 0 to 3. And that's what Simpson's rule needs. The Simpson's rule, the way the Simpson's function works is you give it the x points and the y points. But I can't give it any more x points than I need for the integral. I want to integrate from 0 to x, right? F of t dt. So this x here is really represented by x of I. And just think, as I goes from 0 to 100 and 100, the x value will go from 0 to 6. So it's like a cutoff of the function. So by doing this, I'm only considering things from 0 to 3, and then I'm going to integrate from 0 to 3. All right, so let's see, let me rerun this again. Okay, so I integrate from 0 to x, where x of I is some intermediate value. So this is the mesh point, so I didn't integrate yet. Okay, now I want to, here's where I integrate. Integrate f of t dt. Think of this as f of t dt. Just like this, f of t dt. This is basically f of t dt. But it's only going to x because t is artificially cut off at x. Alright, so I did the integral, and then I need to store that value, because as I change x and x moves, each time x moves, you get a different value for the area. Right? Look at the graph. When x is 0, the area is 0. When x is 1, the area is about up to here. When x is 6, the area is here. So functions are, once again, a collection of x and y values. So I is going to correspond to the mesh point. Remember, y goes from 0 to 100, and as it goes from 0 to 100, x will go from 0 to 6. So once again, think of the I as a way to go from 0 to 6. The I is really like an x value. It's tracing you along the interval, but it does it in 100 steps. So each value of I really corresponds to a value of x. All right, and you want to see what y looks like? You could print it out. And this is it. Okay. All right, so I hope you understood integration. I do recognize, though, this is a little tricky, and though maybe not 100% required for our course, I think it's this will be useful for you to make sure you understand these mesh points a little better. All right, so let's go on to something much easier, the derivative. So once again, we're going to start with linear space. Let's go from 0 to 101. and our goal is to find the derivative of the sine function numerically by using what are called difference quotients. Alright, so how do we do that? It just changes to an n plus 1. I think this is what I wanted. Let's just double check that it works before I try to explain it. No. 101 is out of bounds. Alright. Let me change it here. Alright, I think it's okay now. Okay, so x is going from 0 to 6 again in 101 steps, 100 steps, 101 subdivision points. We're back to the sine of x, and we have it plotted. Alright, so I want the derivative to be y1. Okay, so this time well, it looks like I define y1 to be the linear space from 0 to 6, but then I find its length, and then I rewrite y1 just to be the zeros. And the number of zeros I want there, I think I want n plus 1. Maybe not. Alright, it looks like I might have messed up my program a little bit. Let's see. Alright, let's look at the error. Index 103 is out of bounds. Alright, so why am I looking at 103? Well, what is n? Alright, so perhaps my n's got a little confused. Let's fix n. So n equals 100. Okay. Looks okay to me. X and Y must have the same first dimension. Alright, it looks like I might have messed up this program a little bit. Let me try to undo things so that I get it back to working again. Alright, bear with me for a minute. I might have to go back a little more. Edit, undo. Alright, that's all I could do. Alright, this might be a good exercise trying to figure out what went wrong. Alright, so let's do that. Let's figure out what went wrong. Alright, so I want to take the derivative, so I'm defining my function. It's going to go from 0 to 6, and it's going to use 100 subdivision intervals, 101 subdivision points. Alright, so this is working fine, right? We have our function. Okay, so next I want to get ready for y1. So that's going to hold the derivative. So I need places to store the slope of y. Alright, n is the length of y1. So let's just see what this is. It should be 101, but this is how you can debug and check for errors. Alright, there's y1 there, and let's print its length. So let's see what its length is 102. Alright, this might be the source of our error. See, we were expecting it to be 101, right? Okay, so Alright, let's do something different. Alright, 103. So y is, the length of this is 103. So something seems to be strange, right? Perhaps n is changing somewhere. Alright, n equals 100, and alright, it seems like I fixed it now. It might have been something with n, where there were two different values of n that were mixing things up. Not exactly sure. Alright, so let's take a look. Alright, so y1 is, just to see what y1 looks like. So here's y1, starting at 0, going to 6, and as we expected, there's 101 numbers here, and delta x would be just the distance between consecutive points. Alright, so things look good there. Alright, n is 100. Okay. Now, to calculate the derivative, we use the difference quotients. So notice we have y's and x's here, right? So let's just double check and see what the x's are looking like. So let's look at x. Let's make sure x didn't get corrupted. Alright, x is the same thing, right? We're going from 0 to 6, our standard mesh points. Okay, now in order to calculate the derivative, we're going to use the delta x over delta y. That's exactly this. So I'm going to go to the original function y. Remember what y is. So let's look at y also. So here's y. Remember, that's the sign of the function. So we're going to use the change in y divided by the change in x. So I'm going to look at consecutive y values divided by consecutive x values. Notice I start I at 0, and then I say 0 plus 1 minus y of 0. You don't want to go to negative 1, or that would throw an error. And the same thing for the x's. So, and notice I don't have an answer for y1 of 0. I never get the derivative at 0. I actually just say, let me use the same value when I is 1. Remember, see, these numbers inside here are I values. I ranges from 0 to 101, right? Because those are 0 to 100. This starting at 0 is terribly confusing, but we're stuck with it. So 0 to 100, and each I value corresponds to an x value. Okay, so what I'm saying is the derivative here, I want it to just be the derivative at 0.06. Just because you need an extra point to calculate derivatives. You always need 2 for 1. Alright, so looking at the graph, this is our function, and if we want to change our function, let's go to that more complicated function. Alright, so let's see, where did I define the function? Where did it go? Oh, here it is. Alright, so if you want to change the function, we could just do f of x. Okay, That's the function I defined up there. And then we could do the derivative. And that's the derivative. All right, finally, I want to just help you get ready for what's coming up next in Python is two-dimensional arrays. So a two-dimensional array has two axes, a row and a column. They're considered axis 0 and axis 1. So think of this as a 3 by 3 matrix. Let me display this for you. So it's a 3 by 3 matrix. See how there's double brackets? That means it's a two-dimensional array. Each row is basically a one-dimensional array. It's really an array of arrays. Each row is an array, and then the columns. So each each row is an array, and then the column is an array of rows. Okay, so another way to define arrays. Let's say you have a let's say you want to solve a system of equations. So I want to solve the system of equation here. Ax equals b. So Ax equals b. Alright, so A is a 3 by 3 matrix. B is a column vector, 3 by 1. And X is the answer. X is what we're looking for. So I can define the matrix A like this. This is our 3 by 3 matrix. Notice the double brackets, and notice the 3 rows. Now, I want a column vector, and though it really is just a one-dimensional, array, if you want it to be compatible with your two-dimensional array, your square arrays, your matrices, you need to think of it as a two-dimensional array that's very skinny, that only has really one dimension. So remember, you can consider like a row vector as a 3 by 1 matrix. So it is a two-dimensional array, it's just one of the dimensions is 1.
Yeah, I do. I'm on my lunch break, so have a good day, Jamie.
Alright, so in order to, okay, so we have Ax is equal to b. So here I defined A and I defined B. And then, remember how we solved these using Gaussian elimination? So what we did is we augmented the matrix and added the B column vector into the last column of this new augmented matrix. So that's exactly what we did here. So we have the original 3 by 3 matrix here, and then we have the column vector here. And the idea was to row reduce it. Now, there are fancy ways to do this, but what I really wanted to show you is how to help you get used to using for loops to go through these arrays. How to get inside these elements using loops. All right, so let's give it a try. So I'm going to call this matrix. Let me call this matrix matrix C. All right. All right. So now I have C over there. All right. So first of all, let's we know the dimension of C is 3 rows by 4 columns. For I in range, let's go each row first, 3. for j in range 4. Now I simply want to display each element of the array. So let's print C I, comma j, row, comma column. And as you can see, these are all the elements of the array of the matrix. And just to check, let's print C in its natural form. So there's the matrix in the square format. Rectangular format, that is, right? Okay. So now, remember how we solved these? We want to put it into row echelon form, right? So let's go through row 1 and row 2. Remember, we started counting at 0. Let's turn all of these to 1s. Let's make the pivot column 2, 3, 1. Let's divide the entire matrix by 1. So there is a shortcut. You could just simply divide the whole matrix by 1 in one shot, but let's use the for loop. So I want to divide each column by 1. So for each row, I'm going to go through the column, and I'm going to say Cij is equal to Cij. See, I want to make the 2, 3, 1 into 1s. So what I'm going to do is divide the 0th row by 2, the middle row by 3, and the last row by 1, which I guess we don't really need to, but let's do it anyway. Alright, so I'm going to divide by C. The row number is I, right? And I'm staying in the 0th column. So that's not going to change with j. I'm going to go through the whole row with that same first number. All right, let's see if it works. It did, right? We divided each row by a number in order to turn the numbers in the 0th column all to 1s. All right. Next, let's get rid of these 1s in the first row and the second row, so that we can put it into a triangular form. So what we have to do is say, what we want to do is -1 times row 1 added to row, -1 times row 0 added to row 1, and then do the same thing. -1 times row 0 add to row 2. So let's do that in 2 steps. Alright, so I'm only changing the row 1, right? So I'm just going to say I is 1. That's the row I'm interested in. J is going to change. So for j in range 4, the new value of row I, column j, is equal to the old value of column I, row I, column j, plus I'm going to add -1 times the corresponding column element in row 0, right? So C 0, comma j. Alright, I think this is correct. You could actually do this in a for loop and do 1 and 2 at the same time, but let's see. Alright, so let's see what C looks like, see if we did it correctly. Something is wrong, right? See, we were... Oh, okay, we did change C, right? C has definitely changed, but I think I made a mistake somehow. Alright, so I is 1, so let's try to track down our error, figure out what we did. See if you could figure it out before I do. So let's go back to what C is already. Oh, actually, I can't do this anymore because I'll change things. So I have to go here, and then here. Okay. So this is the value of C right now, right? So I want to take negative of row 0 and add it to row 1, and this is what I got here. As you can see, it's a little tricky dealing with these subscripts. Let me try it again. Oh, now it seemed to work. Perhaps I just had something corrupted. So the code was right. Perhaps it's a bug in the system. Not sure. Sometimes this is a little buggy, just to warn you. Python itself is not buggy, but this Colab is. You know, it's not as well supported as like the real Python. All right, so we were okay. We were fine. So now let's change I to 2. And as you can see, we're in triangular form. And from this point, it's actually pretty easy to solve the system. All right, so I don't want to do this forever. Just wanted to show you. So finally, let me show you how to solve this in real life. So here's another example. We have a 3x3 A matrix. Here's B. There's this neat... One of the great things about Numpy is it does linear algebra for you. It does all this matrix stuff, all the hard work, really fast. So we just have to use this function. Linear algebra solve A x equals B. This is the format. And in one line of code, it basically does what we were doing. It does the Gaussian elimination. All right, so that's it for today. In class, we'll do the finite difference. This is all to get you ready for that kind of stuff. As you can see, the code is a bit complicated here, but we'll get to it. We'll just do it line by line, and we'll understand it. But I think with what I gave you, it should be a lot easier.